Hello everybody. Today I would like to give you the third part of the introductory video for CIS 101. I am Professor Knizhnik and this is the lecture about binary system and how to use in the computer basics. So as I told you folks, transmission of the data is the basis of the telecommunication. And data could be transmitted if you have the source of electricity, like a battery, and a switch. Then it will go far from the transmission area to the area of reception. That is a coil which transmits magnetic field to the anchor. Anchor could be any ferromagnetic element. In our case, it's a key. So plus minus is polarity of the battery, and switch, when it pushed down, the current will go through the wires, and this is conductor. We already know that conductor is provide electrical current. Magnetic field will go around this coil, will capture the key and snap it to the coil. I forgot to introduce the core inside of the coil. The core is amplify the magnetic field, so easier to snap the anchor to the sounder. The sounder is the name of this device, sounder. Why it's sounder? Because when the key is snapped to the magnetic coil, that will be knock sound like this. And for this transmission device was created the specific alphabet. This is Morse code. I told you folks the code is process named encoding, specific process that substitute the real alphabet A, B, C, and so on, Y, Z, to the physical equivalent that could be transmitted through the wires. That is A, that is, let's say, S, and that is O, and so on. So the man who learned this equivalence, meaning encoding or use Morse code, actually operate this switch, and pretty fast. So if you hear this sounder at the reception end, you will hear something like this. Some very talented transmitters transmit about 100 letters per minute. That is pretty fast. Folks, the Morse code actually became very popular, and if you analyze the map of the country that time, so you will find cities which actually connected each to each with wires of the telegraph. Telegraph is the name of this telecommunication system. So all of these cities are connected. I can tell you folks that these communication lines were functioning until the contemporary time. They even was named Internet of 19th century. This apparatus, which is Morse telegraph, were actually everywhere, and in banks, in stock market, and actually everywhere in doctor's office. So that were even like a network, telegraph network. The only problem was to make the secret transmission. Security actually was not working because two humans were involved in both ends. One of them transmit textual information, and another one will receive textual information. So these people were involved in a secret information. If this information about military or bank or stock market. So this situation was problematic. So people start thinking about how to make the transmission and telecommunication system more secure. How to make automatic transmission and automatic reception. So idea to make the transmission a bit secure was connected to the value of the code. Electricity that transmitted to wires has only two valid positions. The electricity is on and electricity is off, meaning electric current go through the wires and through the reception end, or not going. Folks, they named on as 1 and off as 0. Off as 0 also could be interpreted as false in logical sense, and on is true. Why 1 is true and 0 is false? That's easy to understand. If I say I have $5 and I say this is true, multiply by 1, true is 1, that will be still $5. If I have $5, I said $5, but this is false, I will multiply it by 0, by this 0, and that will be 0, meaning lie, I don't have $5. So folks, that is 1 and zeros. 1 and zeros is, again, the voltage and current exist in the telecommunication line or not existing. So how to operate with this, how to transmit alphabetical values through the network of telecommunication lines if we do not have Morse code. Why do not we have Morse code? Because Morse code contains 3 code elements. This is dot, dash, and space. That is 3 elements. But natively, electrical current has 2 elements of the code. One code value and code value 0. So let's try to use just one wire, which is transmit 1 or 0, meaning current is on, current is off, for encoding alphabetical value. So I will open the placeholder, and this placeholder could actually contain either 1 or 0. So we call this value binary. Binary because binary meaning 2. Binary. Binary digit 1 or 0. There is no 3, 4, 5, 6, 7 or more. There is no such thing. So the placeholder for binary information named 1 bit. Folks, 1 bit is elementary unit for measuring information. 1 bit is a true, false, left or right, up and down, on or off. Only 2 values will be encoded. So 1 bit. But 1 bit allows me just to see either 0 or 1. I can use 0 for A and B for 1, and no more alphabetical characters could be involved in the coding. So for 1 bit I have only 2 variations, but my variations are minimum 26 because this is 26 letters in my alphabet. 26 letters. So let's see what's happened. The solution may be 2 bits. Let me take 2 bit, 2 placeholders, and placeholders is like a table cell. I can put either 0 or 1 in them. So that could be 0, 0, 0, 1, 1, 0, and 1, 1. So 2 bit of information will give me 4 variations of the code. And that could be A, that could be B, that could be C, and that could be D, alright? But that's not enough, because 2 bits only 4 combinations. We need at least 26. But folks, 26 are literally not enough. Take a look, we have A, B, C, D, and so on, Z. Small letters. We have capital letters A, B, and Z. We have 1, 2, 0 numbers. We have comma, dot, colon, semicolon, underscore, dash, long dash, slash, backslash, equal sign, root sign, and many others. So I'll tell you folks that total number of English language symbols is 256. 256 symbols. 256 symbols on the keyboard. And I forgot, folks, that the space, the long key on the keyboard. So if this is a keyboard, folks, this is keyboard. The long key here is a space, and this is also symbol. So this symbol must be in use in the encoding of 256 symbols. This is keyboard. What we can do, I suggest to use 3 positions, 3 bits, 3 bit. Let's see what's happened and how many combinations we'll have in this case for 3 bit. This is 000, 001, 010, 011, 100, 101, 110, and 111. And this is only 8 combinations. 8 combinations could be A, B, C, D, and then 4 others. That's not enough. Not enough. Folks, I can see here a little bit something that remind me algebraic depending. Look at this. For 1, it's 2. For 2, it's 4. For 3, it's 8. This is number of combination, quantity of combination. And this is number of bit. Number of bit. This table. You see, it's doubled every time. 1, 2, 2, 4, 3, 8, 4, 4. I believe that will be 16. 16 combinations. So the formula that created according to this dependability is Q, which is number of combinations, is equal to in the power of n, where n is number of bit that we use. This formula, folks, must be remembered because that will be actually on exams. So look at this. Number of combinations for 4. 2 in the power of 4 is 16. It works. So let's see for what number of bits we will have 256 combinations. Again, Q is equal to in the power of n. N is number of bit, Q is number of combinations. If I say n5, so that is 5 bit, 5 bit, then Q will be equal 32. I will remind you folks what is power. If I say 5 bit, that's meaning I need to take 2, multiply by 2, multiply by 2, by 2, and by 2, 5 times, and that is 32. You can calculate. Okay, then for n equal 6, that is 6 bit, Q is 2 in the power of 6, which is equal 64. 64. Not enough. N equals 7. 7 bit. Q will be 2 in the power of 7. 128. 128. Okay, and for n equal 8, that will be 8 bit. Q will be equal 2 in the power of 8, which is 256. 256. So folks, that is a very significant number, 8, because 8 bit is another measurement unit for information, which is equal 1 byte. 1 byte. So all alphabetical letters of English language, as well as Spanish, as well as German, all languages that use Latin letters actually could be represented with this kind of encoding. So let's see how 1 byte looks like in a matter of placeholders. That is 8 placeholders. I will draw them here. 8 placeholders. So each placeholder is 1 bit. Total 8 placeholders is 1 byte. 1 byte. And if I do something like this, 1 0 0 0 0 0 0 1. This is byte, absolutely. Can I say that will be A? Yes. Can I use this 0 0 0 0 0 1 0? Can I say that will be B? Yes. And I have plenty of codes like this 1 0 0 0 0 0 1 1, and that will be C. So I can encode 256 different codes, so 256 different characters. The last one will be 1 1 1 1 1 1 1 1, and I don't remember what symbol is this. So folks, this is principle of encoding, of using the binary code, not a Morse code. Binary code which is zeros and ones. So these code combinations was invented in the beginning of 20th century by the person named Baudot, the French engineer. How this encoding named? And I will tell you folks, the name of this encoding is important because the code table which actually used for encoding must be the same as a code table that used for decoding. Encoding is conversion of real letters to the code. Code is substitution with the digital ones and zeros. Decoding is code transforming to the real letters. But these code tables must be the same. They could be mirror of each other. Otherwise, folks, if the code table is different, the decoding will not be equal of encoding, and you will find abracadabra. You will not find the same letters. Speaking about encoding and decoding, guys, I would like to tell you that the human mouth produce sound is encoding machine. Encoding. Why it's encoding? Because when I say table in my mind, right, in my mind, that will be the idea of table. It will not be table when I speak it. But when I pronounce sounds like table. So I convert the image into the sound, and that is encoding. Now, this sound goes to the somebody with big ear, and within the brain of this person, sound must be converted to images, back to images. So that will be from sound to the image of the table. And this is decoding. So folks, when I use English language to speak to you, that is actually encoding in my brain the images of things that I think about to the sound of things that I transmit to you as a sound. Then sound will be transmitted in your brain to the images of things that we're talking about. And you can imagine these things. Byte is binary information that could be placed in this kind of placeholder, which has small placeholders for 8-bit, and each bit of this byte could be either 0 or 1. So the byte will start with 0, 0, 0, 0, 0, 0, 0. Then it will be 0, 0, 0, 0, 0, 0, 0, 1. Next combination will be 0, 0, 0, 0, 0, 0, 1, 0. And next one will be 0, 0, 0, 0, 0, 0, 1, 1. And so on, folks. So that will go and go and go 256 times. So that will be 256 combinations. And we'll finish with the last possible combination, which will be 1, 1, 1, 1, 1, 1, 1, 1. Okay, total combinations is 256. So we can utilize our formula. Q, number of combinations, is equal to in the power of n, where Q, number of combinations, but n is number of bits. 8-bit, folks, that will be 2 in the power of 8, will be 256. So 256 combinations, designers of the encoding system, they consider that 256 combinations are suitable to place 256 characters of Latin-based languages. How it looks like? The same way like I wrote here. So let's say for A, 1001, 0001. That could be A, then 1001, 0010. That could be B, and so on and so on and so on. I suggest you folks to print this code table. This code table, by the way, has a name, ASCII. ASCII. That name came from the 1930s, and standard code table for English and Spanish and German and other like these languages, and it's named American Standard Code for Information Interchange, ASCII code. So folks, definitely encoding and decoding table must be the same as I told you. So ASCII code for encoding that will be real letters, and that will be binary letters. How many bit for binary? 8-bit for each character. How many characters? 256. That is encoding. As I told you, encoding is substitution from real letters, sounds, and so on to the form suitable for electronic management. Bits and bytes are really suitable for electronic management because there is a lot of devices like lamp which can show you light on and darkness off, electrical current which is on and off, logical true false, and so on. A lot binary devices, transistor, microchips, and so on. So really suitable form for computer management is binary. And then I will put here decoding table. We'll receive 8-bit for each symbol. It will be like this symbol, and that will be real symbol. This is the same ASCII code table for decoding. Folks, what else I can tell you? 256 characters for ASCII code table. Is that good or bad? This is good when you use just English language. But you can use Cyrillic language containing letters like U, C, Sh, and so on. There's no such letters in English language. Then it could be Chinese or Cantonese with hieroglyphical language like this. How many hieroglyphs in Chinese language? More than 3,000. Then, folks, Hebrew language. That will be Beit, that will be Aleph, that will be Greek languages, which looks like this, the same. Then there could be Vietnamese, Cantonese, Japanese, and so on and so on and so on. So it's a lot of languages that need to encode their symbols, especially Internet, international network, Internet connecting country between each other. So we need some kind of table that will be more capable to display and convert electronically more symbols than we already can convert in ASCII code table. So folks, designers of Internet code table, they consider that they need more than 10,000, maybe more than 20,000 symbols to encode. And then they designed the code which utilized 2 bytes per character. 2 bytes per character. Byte 1, byte 2. This code, by the way, 2 bytes at 16-bit. So Q number of combinations for this will be 2 in the power of 16, which is 65,000 approximately. You can calculate it exactly. 65,000 characters, folks, is enough space for encoding table to encode and decode all languages on the earth. And this code, folks, named Unicode. This code used in Internet and it used by browsers, okay? And you can switch from ASCII code to Unicode and vice versa. When we need Unicode, when you get a letter from Chinese or you go to Chinese website which use hieroglyphic letters, or Japanese website or Russian website, in this case you will be able to use Unicode. So that is 8-bit, folks, in each byte, totally 16-bit. Definitely this is from 16 zeros to 16 ones. Total more than 65,000 code lines. Each code line, by the way, folks, each code line is encoding for one symbol. Okay, all of the things I told you just to make sure that you understand that binary system is suitable for encoding textual information. Let me introduce a couple of problems that will be offered you on exams. For example, the book of Bible contain 480,000 of characters. To encode it, we use ASCII code that was encoded and placed on the computer memory. What is the file size? So we need to remember that ASCII code utilized 1 byte per character. 1 byte per character. So how many characters, so many bytes? And we can say 480,000 byte. But folks, this record is not suitable. How to make the more suitable record? So people start working and they design these kind of records. Approximately 1,000 bytes, it is 1 KB, kilobyte. Approximately 1 million bytes, that is 1 MB, 1 megabyte. Approximately 1 billion byte is 1 TB, terabyte. And approximately 1 trillion byte is 1 petabyte. 1 million megabyte, 1 billion terabyte, 1 trillion petabyte. So here, 48 and 3 zeros, we can put comma here. That will be 48 KB. 48 kilobyte is the size of this file. Definitely, folks, if we encode in the code table of Unicode, that will be doubled in size because we have 2 bytes per character in Unicode.